the coffee breaks and the poster sessions. So the next part is the second keynote talk by Dr. Maung. The topic is adversarial attack and defense on vision language models. So this is the bio of Dr. Maung. So he received bachelor degrees from the International LLMs University Malaysia in 2013 under the Abu Khari Foundation Scholarship, and master degrees from the University of Malaya in 2018 under the International Radio Research Assistance Scheme, and a PhD degrees from the Tokyo Metropolitan University in 2022 under the Tokyo Human Resources Fund for City Diplomacy Scholarship. After completing his PhD, he works as a project assistant professor at TMU and as a researcher at Rena Corporations Ltd for 1 year. Currently, he is a project assistant professor at the National Institute of Informatics, Japan. He received the Attributes ICC TWU's Best Paper Award in 2016, and one of his papers was chosen as the Student Journal Paper Award by the IEEE Signal Processing Society, Japan in 2022. His current research focus on foundation model security. So let's welcome Dr. Maung for his keynote talk.
Thank you for the introduction. First of all, thanks for having me. And my name is Pyone. I think probably you read my name, April Pyone Maung, and you are expecting the female. And sorry for confusing you guys. Security people are always tricky. Actually, I was born in April, and somehow my name has April stick with it. Actually, it doesn't mean I changed my gender or not. I didn't change my gender, so I am male. So today I'm from NI again, and okay, it is my first time for an invited talk, and also first time VLM. So I wanted to make it first. I want to explain the topic first. Then I will introduce myself a little bit about me, and then I will tell you what the talk looks like. Okay. So, sorry. I think the title is a bit general. So what we mean by vision language model, even vision language model, there are different kinds of vision language model. So I try to simplify it in this way. So we have the image and we have the text, and you give the model VLM and you get the output. So some application will be like zero-shot image classification, image retrieval, visual questioning, and so on. So just to give you a little bit more clearer, let's look at an example from the Hugging phase. So here is the vision language model, and you give an image. This is the two cats image, and you can do image localization. You said, where is the cat? I cannot read it. Maybe you cannot read it as well. Where the cat exit, it will give you where the cat located. And also you can do segmentation. You can do some sort of like chatting. What is this cat doing? Or you can do some sort of like zero-shot learning with instruction. So this is the tabby cat. So you can ask what this cat is. So it will be something like this. So it's exciting. There are lots of applications with vision language models, and there are so many vision language models. You can look at it in Hugging Face arena. So to give you one more recent example, I'm not sure, maybe you have tried the Llama OCR. I tried before I came to Vienna, and it works pretty well, but the thing is, it doesn't work for the Japanese text. So I live in Japan, so I give the Japanese receipt and it doesn't work. Maybe the Japanese people have an opportunity to improve the Llama OCR for Japanese version. So I think it's enough for the application. So we want to talk basically today two models. And the first one is the clip language image retraining. Basically, you have the text, you have the image, and you learn the joint embedding space. So this clip is actually useful in many things. It becomes like a building block for many other, for example, in stable diffusion also you use it, and also vision condition language models also use it. So the general idea is there are so many, I think, design patterns for VLMs. So today I'm going to focus on this architecture. It is, you have the image encoder basically come from the clip, and it is not trained at all. So usually in VLM, you want to do two-stage training. For the pre-training, you train only the projector, and then you train the text encoder and projector together. And here we call it like vision condition language model, not to confuse with the VLM. I try to make it a little bit different. So it's like pre-training clip and vision language VLM, something like that. Okay, all right. So this is our focus. We are going to focus on these two models. So just to be a little bit more specific and about adversarial thing. So usually robustness research aim to build AI systems that are resilient. So they are basically two branches. One is the black swan, the very rare robustness. I think, for example, it is a distribution shift. So large body of the robustness research fall into this category. And also there is the adversarial side, because this happened in real, I mean, yeah, nobody did it, it happened. So there is in robustness research, there is the same things that have never happened before happen all the time. So we cannot ignore because they are rare cases, but they are also very important. And the other side is the adversary side is one of my professor told me, my name is Pyone, but he kind of called me like Pyone. So is the way he pronounced it. Pyone, he said, we don't need security in the ideal world because security is all about stealing something. And he said, the problem is we don't live in the real world, and we don't live in the ideal world, and we live in the real world. So there are many adversaries with us. So adversary can carefully create something and deceive to fool the system or to cause some harms. So in this talk, we are going to focus on adversarial side, attacks and defense of the previous, this one, the clip and the vision language model. So pretty clear, the title is just attack and defense for this clip and this one. So, okay, so now coming to me. Actually, I don't want to spend too much time on this because I'm afraid after I talk this too long, you will forget what I told about the title. So I will go quickly for the introduction. I study in different university for bachelor, master, and PhD, and I got my PhD in 2022, and currently I'm working as a project assistant professor in NII. And my research focus is the foundation model security. So I believe I can share one or two things in this talk that you can take away. So let's start. This is the agenda for today, a little bit of motivation. And actually, we want to talk about the clip and vision as I promised before. But to do that, I need to start from the classical image classification, the image only model first so that we can have the better understanding of this. So I included this one. And then we talk about the challenges and opportunities. So motivation. So why do we care? So the thing is obvious reason, because we don't live in an ideal world. We live in the real world, and there are so many adversaries. So we want to defend the adversarial attacks. And security research is not just security defending the bad guy, but it goes beyond the security. So we want to understand the model better. For example, like the previous paper talked about adversarial examples are not bugs, they are features. And to make sure what the model is supposed to do to learn better, understand better representation, and so forth. And actually, we want to build the reliable systems. And we also, this is the controversial, so we want to measure the progress, because media and I don't know, companies oversell it. We have already, like, I don't know, a super powerful AI or something. And actually, we do not even have the cat level AI. So recently, the Meta company, they kind of use it, advanced machine intelligence instead of AGI or something like that. So we want to also make sure what is the system, what is the human. Of course, our aim is we want to get the human level intelligence, but we are not, in my opinion, we are not there yet. We are still very far away. So this is the motivation. And in 2018 from the Professor Madri's workshop, he said the state of machine learning security is like this damn starfire. So I watched his talk a lot, and I started my PhD in 2019, and I think he kind of influenced me to do this kind of research for the PhD. So I thought if I can somehow stop a little bit of fire, it might be useful. But after I finished PhD and now, I feel like maybe we have so much fire now in 2024 instead of finishing this. And I will clarify later after the other slides. Okay, so go back to going to the unimodal single modality model image classification. Classical example is adversarial example. This picture is classified correctly as giant panda, and if you add invisible noise, it will be classified as the airline. So I specifically make it because I want to make panda fly. So there is the joke in the machine learning security research. We said in machine learning, nothing is impossible. We can do anything. So even panda can fly. So just like a little bit technical. So the previous classifier that what I saw that we fooled is basically the neural network classifier, and you have like basically it is the supervised learning test, and you have the bunch of the images and their labels, and you try to learn this function by using like empirical risk minimization. For example, this case, the common choice is the cross entropy loss. So there are two kinds of adversarial example. Actually, there are so many, so many classifications. There are many papers talk about white box, black box, something, and very few papers talk categorized in this way. So I thought it is worth sharing today to classify this way. This one is perturbation based. Basically, you are finding adversarial example within certain bound, and that adversarial example can fool the network, but it doesn't fool the oracle. For example, in this case, oracle is the human. So if you see the previous panda, in our eyes, panda is always panda, but in the neural network eyes, it is the airliner. So this is the definition of the perturbation-based adversarial example. This is come from this paper. I personally like this notation because it captures everything. And this is important because we need to do the principal research. So this gives us a lot of advantage for doing research. But in real life, we cannot say to the adversary, please attack us with only this perturbation-based adversarial example. We cannot do the real attackers do not compute gradients. So we have to consider the unrestricted adversarial example case as well. This is more general and more practical. So there are two kinds of adversarial example, but in this talk, we will only focus on this because it is good for research. So there are several applications. I think you have seen this before. It is the private sign classification. You put some sticker and you can fool the system. And this is the 3D generate 3D printed turtle, and it classifies wrongly all the time. This is the face recognition system. This is the object detection. I think there are more new ones. This may be a little bit old applications, just to give you an idea. So for defense, how to defend? There are two major strategies for designing a defense. The first defense is like adversarial training. The idea is to be robust against all adversarial example in a specified adversarial space. For example, I showed you before about the non-bounded non-bounded adversarial example. In this case, you train the model with maybe certain non-bound, and we kind of hope that the model will be robust within that bound. So we can basically, this is the formulation, but we cannot solve this problem. So we kind of estimated empirically, we can do projected gradient descent in the training to find the adversarial example here. And also we have some sort of certified defense way in a certified way. This is kind of like a major main body of the defense work. There are so many variants of the adversarial training papers. Another strategy is make adversarial attacks ineffective from the computational hardness perspective, because assume if you can detect the adversarial example, you can reject it. But the thing is, there are many applications, we cannot reject it. We have to somehow give. So this is kind of not the defense, but we can still say, hey, there is an example coming, I don't understand. The model can choose, I don't understand or something, and it can reject it. So another one is the input transformation. This is also like to make the adversarial noise weaker by using the several transformation. And the last one is key-based. So adversarial defense research is like a cat and mouse game, and it is attack and defense like competing each other. We have the new attack, we have the new defense, new attack game, new defense game. It is never ending. So we should learn from the cryptography. So in the second Kakos principle says the system can be known, but the key should be secret. So based on that principle, we kind of do something different from the previous defense. What we did was, okay, basically, let's consider to find an attack idea. Attack idea is, if you want to find the attack, you have to know the model decision. If you don't know the model decision, you cannot optimize your adversarial example. You have to somehow know it. If you don't know, you have to approximate. That's the basic requirement of making an attack work. But so what do? We can kind of hide the correct output from the model to defend. So what we do is, instead of the previous transformation, there are so many transformations, but they are not safe, they are broken. So we kind of put the secret key, and instead of training the model with X, we train the model with H. So assuming that the model understands only H, if the H is somehow controlled with the secret key, the attacker cannot attack very well. This is our kind of our thinking. So this is an example of the H, example of how we can do like this. For example, in this case, you divide an image into blocks, and each block is shuffled in the block. So for example, block size 4, you shuffle the pixel in 4, all blocks. And this is 4, this is 8, this is 16, 32. So what happened is, when you train the model with this kind of images, the model somehow learned your blocky, this secret pattern. So without that secret pattern, the model cannot predict correctly. So that's the idea. And the result is like this. So we somehow, I think this is the ImageNet result. We somehow can defend the adversarial example, like if the perturbation is small, but if the perturbation is so much, then we cannot defend it. Why? Because the perturbation overruled the secret patterns that we overlay in the previous, like this. The perturbation has more effect, so it doesn't work. So still, this key-based defense is also not practical and not working. And this is the example of the key-based boundary. For example, if this is trained with the key 1, key 2, key 3, you get the similar performance, but your decision boundaries are not the same. So if attacker is attacking this decision boundary, it doesn't work very well here. But if you use large perturbation, it works everywhere. So that's the limitation. And okay, so this is the idea. I just talk about the image classification model and attacks and defense. So attack is we have the part non-bounded part of adversarial example and restricted adversarial example. And for the defense, you have two major strategy. One is you can do adversarial training, and one is based on the computational hardness, you can control the secret key, or you can do image input transformation, or several things. So moving to the clip, that's what we want to talk about. The clip attack is called typographic attack. This is the built-in vulnerability. If you try the clip model zero-shot classification, you give this image with this the mouse sticker here, the model will give you the mouse, not dog. So this is clip built-in vulnerability, because clip is trained with the text and image joint to learn joint abundant space. So it makes sense that the model say it mouse. So how do we defend? There is the database like this for the typography attack. So how do we defend it? I think you know stable diffusion, and I'm not sure the drain boot. Drain boot is the stable diffusion, like subject-driven personalization. I think the idea is similar to the stable diffusion dream boot method. That they call it the class prefix learning. What they do is like a stable diffusion dream boot, they are learning the new token, new unique token. And if you give this token to the model in front of the class, you don't have that previous typographic problem. So how do we learn this token? They do it in this way. So you have the adversarial image. This adversarial image is basically the image with the sticker, the some text, and you try to get the cosine similarity, so you will get the probability. And then you use the label and you try to get cross entropy loss. And this, they call it defense loss. This loss plus, and they want to also maintain the model previous knowledge. So they try to do it with the clean image. So you get the clean image probability with the with token and without token, and they try to find the KL divergence, and they do it together. So in stable diffusion dream boot, it's called class prior preservation loss or something. So the idea is almost the same, just here is for the defending the typographic attack. So previously, to defend typographic attack, this paper, there are several methods exist, like for adversarial training or fine-tuning or whatever. The problem is if you fine-tune the model, it will affect your downstream test. So that's why they don't fine-tune. Those models are all frozen. Only one token is learned. So in their way, they show they have good results for everything. So they also have good results for the object detection test, and also good result for the classification test. And yeah, like this. So without their prefix, the models, I think you cannot see it. They cannot, the model classify wrongly because of the text overlay, and with their token, it works. But this is one type of the defense for the typographic attack. And moving on to the another one is the recent work is called the robust clip. So what robust clip test is similar to adversarial training, the similar formulation. They try to fine-tune the model. Yeah, they try to fine-tune the model with the idea is they want to make they retain the original model, and this is the fine-tuned model, and they try to get the previous origin embedding and this embedding close together. And so this way, they call it unsupervised fine-tuning. This way, you don't need the text to fine-tune it, and their results is also not so bad. It has some, for using noise budget 2 and 4, in noise budget 4, they have the performance increase, but 2, they don't have the performance increase. So, and they show for zero-shot classification for many data set. And also, they also show the another for large language model, vision condition large language model also. I'm going to show these things after that. So I mean, this part, I just want to focus on the clip. So what I did in this clip is I show you the typographic attack, and I show you two defense. One is the prefix learning, and one is the adversarial training, basically unsupervised adversarial training, robust clip. So I'm going to move on to the for the vision condition LLM. So I think you all know that LLM, this now is the LLM era. So attacker can harm the LLM. So there is a famous like jailbreaking attack, so many jailbreaking attack, prompt injection attack. So we all know that an attacker, an adversary can harm the LLM model. So there's also another way. Attacker can also harm the honest user. So what he can do is he can upload, for example, can generate adversarial example and upload it to the social network, and the honest users download maybe capture something from the social, for example, like image. And if the image gives to the LLM, he might get like guiding them to malicious website or some fake information or something. I'm going to show you an example. So the idea is attacker not only can harm the LLM model, it also can harm the other users. So here is an example. Look at this one. This is the tower. If you ask the model what is the description of this image, it will give you the Eiffel Tower. I think this is maybe they choose the image captioning model. And if you apply the noise, like adversarial example, the same techniques, the one I show you, the first, very first adversarial example thing is like a projected gradient descent or something. If you apply this to this auto-regressive objective to optimize this targeted text, what happens is when you ask the model, what is this image? The model will tell you, visit this URL. So this URL can be a malicious website that can install malware or something that can lead you. So this is example of how the attacker can harm the user. So this is basically straightforward because we just transfer the previous adversarial example concept to the vision language model. And these are some examples. For example, this is a patient in the hospital, but after you optimize, you make it as an adversarial example, it becomes like something with the vaccination, or it gives you some misinformation or some fake information. Idea the same. So here it is Times Square, but it gives you some weird, or here is the Joe Biden, it gives you Joe Biden give the nuclear strike, or here financial market are crashing or something. So it gives you some sort of like, I don't know, fake information that you will emotionally move, something like that. So this is straightforward. So we can do better because if we do this way, previous this way to find adversarial example, sometimes the models are big and it cannot fit in our GPU and we cannot compute the gradient. And this is basically challenging. It's basically sometimes not possible. So we can do better. Recent attacks. I want to introduce the attack VLM. So there are three strategies for the attack VLM. One is the image matching image features, matching image text feature, matching text feature. So what they do is, the idea is they are basically, instead of attacking the VLM, they are attacking only the image encoder. So you try to, I will explain with the picture, it is much better. Okay, so sorry for the small text, I try to explain it. So for example, you have the text, targeted text you want to convey, maybe this is the fake information or something. So what the attack VLM does is it converts the text to the image. So by using, for example, Stable Diffusion or DALL-E or whatever, so you get the targeted image and you have the clean image. Basically, what you're doing is you try to match the embedding of this targeted image and the embedding of this clean image. So you match like that, and you have some, you can optimize some noise and you add it here. So what happened is when you do that, this is the original inference. So text to image, you give to the image to text, sorry, then it will give you colorful painting or something. But after adding noise, it will give you this one here, the C something, the targeted text you give will be here. So similar to this is the image to image matching. So image to text matching, this is, I think, image to text matching. Because basically, image to text matching is, it is not gradient based because commercial LLM are not accessible. So they try to query the black box LLM and they try to use random gradient free method to optimize the noise. And the idea is the same. So you're trying to embed this targeted text features into the image so that the targeted model will tell you that the targeted text. So this is their experiments. They are using the ImageNet images from ImageNet, and they are totally irrelevant text from the MS Coco. So different data set, we get the images, one from the text, and we convert this text to the image. Sorry. So these are the results. So after this is this targeted text converted to image, and you run the attack VLM, and this is the adversarial example, and it will give you, the text will give you something like that. This is similar example. So they calculate the image and the targeted text similarity score. And you can see if you calculate clean image and the targeted text, because clean image and targeted text are irrelevant. So the score is very bad. And this is the generated image like stable diffusion or something with the targeted text. So the similarity scores get better, and they find image to text, they are in their image to text strategy, get the highest score for the adversarial image is much closer to the targeted test. So this is their result. Another one is, I think this is also important. So I also want to share this attack. So in real world, I think we cannot do the white box gradient-based attack. And what we can do is we assume we have several models and we try to transfer, for example, there are open source model available. So you generate adversarial example on the models you have, and then you want to transfer that adversarial example to the targeted model. So this is the pretty known technique to have better transfer attack. What you do is you have a couple of models and you try to maybe you average the logits, or you try to, in your optimization, you basically use several models to do a better transfer attack. So this paper, what they do is adversarial example generation is similar to the empirical risk minimization. So they try to learn issues from the risk minimization, and they said that if the loss landscape is flat and close to the local minimum, if we can encourage this common weakness, they said they can do better for the transfer attack for the C2A. So what they do is they use the SAM, sharpness aware minimization, and they have the cosine similarity encourager to kind of get these two properties. And they tested on so many models from the LLMs to the VID-based model, and they find that their CWA attack is 86% attack success rate. And also, not only the clean model, they also try to the adversarially trained model, and they get 55% attack success rate. And also they try input transformation-based defense method, and their attack is 100% successful. So you can see the input transformation-based methods are basically broken. And they also try the VLM, Google's BERT, and they find out if they put too much noise, like 32, and they have very good attack success rate. So they tested 3 scenarios, misdescription, blindness, and the refusal. So I want to show you what is, example of misdescription, blindness, and refusal. So here it looks like, so you give this image and you describe that image, and it will give you totally irrelevant description. This is the misdescription, and also blindness. If you give this image with the adverse, because they use 32/255 noise, so the noise is kind of visible background, some patterns behind, and it will tell you, I cannot describe the image, blindness. And also for refusal, it says, sorry, I cannot something, I cannot read it. So it just refusing to follow the instruction that you ask, or the question you ask. This is the example. So CWA is very good at they have very clever tricks, very nice tricks, and they kind of generate the very robust adversarial example, and it works pretty well for the image classification scenario and also the VLM scenario. So learning from the previous two, so the attack VLM and the attack VLM and the CWA, we try to do something in our institute. The intern student try to improve a little bit. So what we do is we borrow attack VLM. So we have the text, and the text is converted to the image, and we want to match this image embedding and the adversarial image, the clean image. So this is the clean image, but of course it is in the clean image here. So we want to match those two embeddings, but the idea is we also learn from the CWA, because CWA is not the single model attack. It has the multiple surrogates and it transfers better. So we are doing multiple VIT surrogate model and use the CWA optimization, like sharpness aware optimization and also cosine similarity. We use the CWA optimization, and we use the attack VLM objective, and we do not add noise to every pixel. So what we do is we generate the attention mask, and we only perturb the certain area because we don't want to perturb the whole image. We want to make it as invisible as possible. So we add some noise based on the attention mask, and we so we present this in the simple conference, and this is the result we got. So we kind of because I think we did a little bit different from the attack VLM. Attack VLM measure the image and the text similar, the targeted text similarity, because in their case, the targeted text is short. So in our case, we are attacking the LLaVA and mini GPT-4, and the output is very long sometimes. So it doesn't work well with the clip score. So we are using the sentence bar scores to measure the targeted text and the targeted text output and adversarial output, and we lost a little bit. So our attack doesn't have the very good attack success rate, but on the other hand, we have the good quality. We also measure the image quality, so we have better quality, but we sacrifice a little bit of attack success rate. So this is an example of the attacking with the rollout attention mask, and we give this is the targeted text, and we get the image, and then we generate adversarial example, and the model output will reflect this targeted text. This is another example, but this time not rollout attention. We use the layer wise relevance propagation attention mask. This is for the LLaVA, and this is for the mini GPT-4. So the good thing about this is our method, in one adversarial example, we can attack two models at the same time because we have the multiple surrogate models, and one adversarial example can work for the multiple models, and also we have less noise. This is for the mini GPT-4. I think it's similar scenario. So moving on to the robust clip, we have already seen that robust clip before. Robust clip is basically adversarial training, and unsupervised adversarial training. You kind of make the embedding of the adversarial example and the clean image as close as possible, and you generate adversarial. You maximize the adversarial noise in the training. It also applicable to the other large vision language model. So they tested the LLaVA with 2/255, and this is 4/255. And there are several tests they target. For example, like you can fool it, you put email API or vaccines are dangerous, something. So they kind of do this kind of experiments. And they found out that if you use the simple clip, attack success rate is 100%. But if you use their proposed method, it cannot fool because they basically, their defense is good. So attack success rate becomes, sorry, this is mean success rate. Yeah, so the attack cannot work on their defendant model. So this is an example. So here is an original image, and you give the normal clip. If you use normal clip in LLaVA, because LLaVA has the clip component, and you will get the busy city street filled with people and traffic. And this is the previous supervised fine-tuned adversarial training, and it also gives you the similar meaning, similar description. And this is the robust clip, the fair loss. It gives you. So this is plain image. But if you give adversarial image, and the first one doesn't work at all, it will give you visit this URL. So basically, this is what attacker wants. And this one also works. This is the adversarial training, but the description doesn't reflect to the original description. And the fair loss, the robust clip gives you the almost similar the description. So what they are trying to say here is their robust clip, it works for the image classification, and also it works for the downstream text like the LLaVA or other VLM text, and let's compare it to the previous adversarial training method. So this is one defense for the VLM is robust clip, and it is also recent. And this is another example. So the target is sell your stocks and financial markets are crashing and you will give like this and just attack the stuff like this. So I think you get the idea of what I'm trying to say. Okay, so actually, when I was making the slide, I was thinking not to include this one because this is the recent one and I haven't tried this yet. But I think this is the only practical defense I have ever seen. So I think it is worth sharing with you guys. So this is called recent attack circuit breaking. Actually, this is the design for the LLM. The idea is not for image classification. They are also, this defense is for LLM outputting the harmful output. So they are basically designed for the LLM for safety reason. The idea is they call it representation rerouting. What they do is they try to get out harmful outputs and they try to get the representation and remap what representation are responsible for the harmful output and they reroute it. So that's what they do. And it shows no sacrifice to the model performance. So as we have seen, adversarial training has a lot of problems. And in real world, I think adversarial training is almost never used in real world. So it is hopeful because this is the first time I see the defense can be used in the real world. And they even, they started a company and they released the model called Signet for the LLM. And they, in their paper, they also say that thing also works for the multimodal. So they also try the multimodal and that multimodal output the harmful output. So basically, this is for safety purpose. And I think security and safety all overlap a lot. So I think this, I find it is hopeful defense. Maybe you can, I don't know, get into detail if you want to see about this thing. So this circuit breaking. So I think I planned 40 minutes, so it's 40 minutes, but I still have maybe the last session. So I think this is the most important one. So challenges. So as I said before, I have shared like key attacks and defense for the CLIP and for the VLMs, and traditional attacks against large models on the conceivable language GPUs are not possible. If the models are large, for sure, you cannot even put it in your GPU and it doesn't work to propagate and compute the gradients. And there are a lot of things not practical. And practical black box attacks are still challenging because as I said, as I showed you before, the attacker generate adversarial example and upload it to the social network and the honest user download that image. Most probably it is not practical and it will not work because the social network use a lot of compression techniques and they may be they compress multiple times and your noise will probably be gone. But it doesn't mean it is not practical because attacker can generate the robust adversarial example that can survive the compressions and a lot of things. So we still need to care about that thing, that kind of threat scenario. But however, we need to come up with the practical black box attack. What are the practical attacks that, then also recent large models are getting more complex with better capabilities and also agentic flow. So you have lots of agentic design patterns and how can you attack those things. And also, I think it is even more dangerous because LLM these days can do function call and nowadays can do even computer use or some other thing. So the attacks are even much more practical now. Previously, if you generate adversarial example and you fool the classifier, it doesn't actually give any harmful. I haven't seen any self-driving car crash because of adversarial example or something. And also, but for this kind of things, if you are using, for example, function call and your function call has the email API something, and you can trick the model to get into your inbox and get steal some information from your email. Or I think there are some real world hacking scenario exists in this agentic workflow and recent AI agents. And as I have shown you before, adversarial training has a lot of problems because it is to date, up to now, it is the most robust, empirically robust technique. But the problem is it has the significant trade-off between the robustness and utility. So your performance drop like 50%. So that's why it is never used in real life. And also it will fail to generalize insane attacks. So you have it is non-bounded. So basically, for example, you train adversarial example with maximum non-bound, and you can attack that model with L1 or some other tricks you can do. And so basically it's not practical, it cannot generalize. And also it's computationally expensive because you have two min-max optimization. So inside the max, you have to generate adversarial example. That generating step is not cheap. So it is somehow not, it is still challenging. So this is the difficulties we have for attacking. Actually, sorry, I know more about the attacks than defense because I am currently working on it's not that, I mean, of course I want to defend, but how to say, defend is more difficult. So maybe I share more about the attacks more in this talk, but of course we want to, I want to say it is challenging for defense. And opportunities, yeah. Now I think machine learning paradigm shift is towards the foundation model. So everybody is talking about foundation model. There are many companies, and before people, companies use machine learning. Maybe your phone has some sort of like image recognition or something, but you don't directly use the machine learning. But these days in this room, I'm 100% sure that everybody use ChatGPT on a weekly basis or even maybe daily basis, or maybe you are using, you can see the statistics that ChatGPT released, and there are so many users in a short amount of time. So the shift is towards individual usage. I think in the future, everyone has their own AI agent, and you will use the AI agents more. So the more we use, if the model is widely used, it is the opportunity for the security people, because we don't live in the ideal world, we live in the real world. So there are a lot of opportunities for now. Even, that's the best time to do the security research. And yes, multimodals are widely used. There's a demand for security, and realistic threat models are in need. As I said before, we have so many papers, I think exponentially increasing you type adversarial example paper. I don't know, I think I cannot read even every day new papers coming. And so most of them are not realistic. So just to be honest, so we need some realistic models are in need, and defense model are still not good enough. And of course, security research is fun. So it is like solving the puzzle. So if you can solve the puzzle, you feel good, you feel fun. So I think that's one of the motivation I have to do this research. And security research make you understand the model better. So you will build, you have better insight, so you can build the better model, better reliable system. I think that's all I have. I just want to share. I think the time is also 46 minutes. I think maybe on time, I guess. And yeah, thank you for listening.
Well, thank you very much for your talk. The audience, do you have any questions for Dr. Maung? We have a fun question for you. So what do you think about the companies doing business with the vision language model? Do you think that they implement the defense mechanism for such kind of model?
It's a good question. I think, for example, I don't know about the companies, because the companies we cannot see, they are not transparent. But if you look at the recent Llama 3.2 vision model, it comes with the built-in guardrail. So it will maybe how to say, filter some output or filter some input. There are some sort of filtering mechanism built in, but of course it can be bypassed easily. For example, Signet, I told you before, Signet is kind of like the best model, and they even make a company of the Signet, and it was broken within 24 hours. So it doesn't even survive for 24 hours, and for the LLM case. So I think it is even how to say, much more wide open for the vision domain. There are a lot of things we can do to fool the model. So I don't know about how they do the defense. Yeah. So that's what I can say.
Yeah, thank you. So do you have any additional questions? Yes.
So in adversarial, so I'm not, to be honest, I'm not super familiar with adversarial attack, but, so different models will have different weaknesses, right? So is it even feasible to design an effective adversarial defense mechanism that, are not just specific for a small number of models, but like can work for maybe a meaningfully large enough number of models?
Thank you for the question. Yes, it's a good question. Yes, I think for now, it's not feasible to kind of defend. We don't know the threat mode. We don't know the attack, but I mean, in security research, so many security problems are from the design phase. So when you are designing the model, and if you take consideration of some previous things or something, you can build the better system. So our hope is we want to build better reliable system. So we have to, we have to start from something. So you can, for example, like internet was not designed like this. So a lot of problems and exploits are every day. And so I think we can learn from what internet has been through, and for AI. So that's what we are trying to do, I guess. So I think maybe it's not, we cannot have like a gold standard defense, because different tests, different things, different everything. But we have to do our best to build better and better and better reliable systems. So thank you.